section 6.6, non-conservative forces and the work-energy theorem. So once again, looking at the work-energy theorem, it says that the work done by non-conservative forces is the final energy minus the initial energy. And we know that the final energy consists of final potential energy plus final kinetic energy. The initial energy that's being subtracted from the final energy is the initial potential plus the initial kinetic energy. And if there's work being done by the non-conservative forces, they'll tell you how the energy changes. So we can solve problems where this work done by non-conservative forces is not zero, as it was in the last section when we had conservation of mechanical energy. Let's see an example of that. So example 11, fireworks. Assuming that the non-conservative force generated by the burning propellant does 425 joules of work, what is the final speed of the rocket? Ignore air resistance. So this one has a lot of the information packed into the picture, right, where we have a rocket, mass of 0.2 kilograms, initial velocity 0, difference in height of 29 meters, and then there's this final velocity that we want to find for it going up that 29 meters. It also tells us we can ignore air resistance, which is a handy thing. And then there's this 425 joules of work. Notice that's 425 joules of work done by the non-conservative force. And this is often how problems that involve non-conservative forces doing work are set up, where they tell you how much work is done by the non-conservative force, or you solve for it explicitly. So it's not something you usually have an equation for with the non-conservative work, unless it's just our standard work equation, force cosine theta times the displacement. So we're going to go to that work-energy theorem and use this 425 joules as our work done by non-conservative forces. So that's what I want you to hold in mind. So as we look at this, we have our work-energy theorem, and we can notice that since the initial velocity is 0, this term is going to go to 0. The other thing to notice is that they give us the difference in height. So it's not h final, nor is it h initial, but it's actually h final minus h initial is equal to 29. So with that in mind, we're going to group the potential energy terms together. mgh final minus mgh initial. So we can pull the mgh, and then we have h final minus h initial, which is just our 29 meters. And as we look at this, we know the mass, we know g, we know that 29 meters, we know the work done by non-conservative forces is 425 joules. The only thing we don't know is this final speed. And that's exactly what we're trying to solve. So if we plug in all the knowns, we can rearrange algebraically the numbers to solve for our final speed. And you should find that it is 61 meters per second. That is pretty quick. But this highlights how these sorts of problems work, where, as mentioned, they often just tell you outright that the work done by the non-conservative forces is blank, or you're trying to solve for it. So that brings us through this section.